This talk is going to be in a few different sections. I'm going to start off talking about the actual radioactive waste material here in the UK, a little bit in general about disposal of radioactive waste, and then finally I'll be moving on to my actual postdoctoral research with Dan in the lab here in Liverpool. So what we're doing here is mapping the yield strength of different mudstones to try and understand if they would be suitable for geological disposal of this radioactive waste. Among nuclear-powered states, the UK has quite a complicated inventory of radioactive waste. So the most obvious component of that is from nuclear power reactors. So nuclear power currently accounts for 15% of our electricity budget in the UK, but the aim of the government is for that to increase to 25% by, I think, 2050. So we have multiple generations of nuclear power reactor configurations from the past 100 years. So we had the earlier Magnox reactors, which were quite inefficient. We now have gas-regulated nuclear power reactors. And then in the future, we're going to be moving more into the small modular reactors. So whilst these are much smaller, they still output about a third of a nuclear reactor, such as the ones at Hinkley Point or Sizewell. The problem is for the UK that in the next 10 years, so between 2026 and 2035, we're actually going to be decommissioning 5 of our nuclear power stations. So we're going to be getting a lot more radioactive waste that needs to be disposed of in the next 10, 20 years or so. Our radioactive waste doesn't only come from our own nuclear power stations. We also have several agreements internationally to both store and process fuel and radioactive waste from other countries. So, for instance, we are storing plutonium for Japan. We also actually do enrichment of uranium for a lot of other nuclear-powered countries for their fuel. So the process of creating this enriched uranium or plutonium, that creates radioactive waste as well. We also get it from medical and industrial sources. So for instance, consumables in the medical industry, these need to be disposed of. There's also research facilities. So there's one on the south coast near where my parents live at Winfrith, Newborough. That's been around for, I think, 100 years or so. We also have, obviously, the Ministry of Defence. We have some nuclear-powered submarines, and we have our nuclear weapons program as well. So any waste from any of these sources could be requiring disposal. So in general, we talk about radioactive waste disposal rather than just nuclear waste disposal. The UK has to run an inventory every few years to understand how much radioactive waste it has. The latest one was in 2022, and there was in total 4.5 million cubic meters of radioactive waste. But of that, only 337,000 meters cubed needs to be permanently disposed of in isolation from the biosphere. So much of the other parts of the radioactive waste inventory, they can be treated, they can be stored in low-level radioactive waste depositories. And in the UK, we have 2 different categories for our radioactive waste. We have low heat generating waste. So those are the top ones on this list here. So these are things like the medical consumables, perhaps sections of nuclear power plants that were quite shielded from the radiation. And we also have high heat generating waste. So this will be things like the fuel rods, plutonium, that needs to be fully isolated away from us in the biosphere. So for some of our material that we have, it's currently stored in storage ponds, such as this Magnox storage pond in Sellafield. So the material is housed inside concrete blocks that are then kept in cooling, very deep water tanks. But over the lifespan of these radioactive materials, so these can be releasing radiation for millions of years, this is not really a long-term storage solution. So we're trying to find other solutions for this. So humans have been using radioactive material for various different purposes for well over 100 years now. So we have to think about what we used to do in the past for historical disposal. Originally, people were using the deep ocean as a disposal site. We don't really know much about the deep ocean. We know more about the surface of the moon. So it was thought in the 1940s this would be a good place to isolate the radioactive waste from us. So the first radioactive waste was dumped 80 kilometers off the coast of California in the Pacific. This went on for quite a few decades. It was decided in 1972 in London that they were going to start regulating this. And then finally in 1994, radioactive waste disposal at sea was completely banned. So it's quite interesting the more you look into this. So I've got an example of the Arctic Ocean here. So the USSR was using the Arctic Ocean as its main dumping ground for all of its radioactive waste. So they had the areas shown here in yellow are where they released liquid radioactive waste. And then I have a few individual sites for where different material was disposed of. So of all the high-level gamma radiation that's released in the Arctic from this material, 90% of it comes from just 6 objects. So we have several nuclear submarines, some of which were sunk on purpose, and some of them, like K159 here, were sunk accidentally. So they were trying to move it somewhere else to then dispose of it correctly, but it sunk just off the coast of Murmansk. We also have sections of the nuclear submarines. So the actual reactors, they sunk off the coast of Novaya Zemlya. And some of these are only in 10 to 20 meters worth of water, and they're just off the coast of this, I think, uninhabited island. So there was a plan in 2021 between Russia and several of the Scandinavian states, including Finland and Norway, to lift this material and dispose of it more safely. But then in 2022, Russia invaded Ukraine and international relations broke down. And there is currently no agreement in how to deal with this material that's there in the Arctic. The Russians say that they will remove it, but there's no real logistical plan for that at the moment. So I got some of this information from the Bologna Foundation, which is a charity that looks into environmental case studies like this. If you're interested, I recommend going and having a look. It's definitely something you can end up having a deep dive on. So for the future, moving forward, the International Atomic Energy Agency recommends geological disposal as the safest method for disposing of radioactive waste. So geological disposal means putting solid radioactive waste into an underground facility that's in a stable rock type, and it's able to provide long-term isolation of that radioactive waste from the biosphere. So they use the term disposal specifically because there's no intention to go and retrieve that waste. Once it's down there, we're not going back to get it. In a geological disposal facility, they have different barriers around the radioactive waste. So the first one is the engineered barrier. So that in this diagram from Posiva, which is the company running disposal in Finland, they have the example of the engineered barriers here with the fuel rod or other solid radioactive waste that's contained within a copper canister. Then this is placed into a small tunnel that is backfilled with bentonite clay. Bentonite massively swells when it comes into contact with water, so it will contain any leakage that comes out of the canister. The next barrier that we have, the one that we're interested in, is the geological barrier, so the actual rock that the canister is contained within. So in the UK, the depth that we're given as guidance within the bedrock is 200 to 1,000 meters deep. And in the UK, we're looking to dispose of our material offshore as well. There are 3 different rock types that are recommended for radioactive waste disposal. The first one are high-strength crystalline rocks. So this is things like granites and gneisses. So they are very high strength and they have high heat capacity, so they won't be affected by the heat emitted during the from the radiation from the material. The issue with them is that when they do break, they're quite brittle and they tend not to seal the fractures so quickly afterwards. So whilst when they're intact, they have very low permeability. If you then break them, the fracture pathways could provide quite an increase in permeability. The next rock type is evaporites. So this is one that's being used in New Mexico in the USA and in Germany as well as disposal facilities. So these are, in contrast, these are very low strength, but because they flow ductilely when they break, they can seal any fractures that are created. So they have very low permeability. The issue with these is that they do flow and they are buoyant, tend to be in the Earth's crust. So then it's quite difficult to model how they're going to react long term. The final type of rock for GDFs is low strength sediments. So this can include mudstones, siltstones. These are very low strength. So the issue we have with these is that it'd be quite an engineering challenge to create a GDF. But they are very low permeability, low porosity, and because they contain clay minerals, they have very good fracture sealing capacity due to the swelling of the clays. And they also have the added bonus that clays can adsorb radionuclides into their structure and actually remove those from any contaminated water. The UK is in the early stages of trying to develop a GDF, but there are other countries that are further ahead of us. So an example here is Finland. They have built a disposal facility on the island of Olkiluoto. So they actually already have a decommissioned nuclear power plant there, so it makes it very easy to transport the waste. And they only have one other nuclear power station currently in operation at Loviisa here. So the rock types that they've used, that they've targeted are very strong crystalline rocks. So it's granitic pegmatites, gneisses, migmatites. So they have a very strong structural fabric. And they are actually in the later stages of building this disposal facility. So they will be hoping to get material into the facility within the next few years. So these like tunnels that you can see built into here, these are the actual tunnels that the material will be placed into, whereas this is one of the access tunnels here. And they have done a huge amount of characterization of the rock types, including looking at the structural fabrics, fracture networks, and the different rock types. Here in the UK, our disposal program is managed by Nuclear Waste Services. They used to be called NIREX, but they've changed their name. And then the disposal program in Scotland is managed separately due to the devolved powers. So when I talk about UK disposal, I'm actually talking about England and Wales here. So where we are in the process, we are somewhere in this early stage of search areas and site evaluation. So NWS's siting factors that they're using to choose where the GDF will go are based on, firstly, they need a willing community to host the GDF. And then after that, they need to know that actually a GDF will be feasible and it will have good transport links for bringing any waste material to the site. And they need to know that the geology is going to be suitable. And also, obviously, value for money at the moment. So how I fit into all of this is that I am part of a large research consortium called GeoSafe, and we are looking towards safe geological disposal of radioactive waste in low-strength sedimentary rocks. So we're a large research consortium across the UK. So we have partners in Heriot-Watt, in Manchester, Leeds, Imperial College London, and then we also have some corporate partners as well, so Nuclear Waste Services themselves, the BGS, UK NNL, and we also have a few international observers, I suppose, assisting us. So we have the Swiss disposal program, the equivalent of NWS, NAGRA, and we also have the Finnish Geological Survey as well, GTK. So they're helping to advise us. So whilst we are doing research on radioactive waste disposal, our research won't be actually informing which site is chosen. Our understanding will feed more into the safety case of trying to understand if the site that NWS picks, will that be a safe site? The two rock types that we're looking at in GeoSafe are two end-member low-strength sedimentary rocks. So on one hand, we have the Triassic Mercia Mudstone Group. So this is a continental rock type. It's fine-grained, it's siliciclastic, and it has a lot of evaporite material in it, so gypsum and hydrite and halites. The other end of the spectrum is the Ancholme Group. So this is Jurassic. It is a marine mudstone. It's very rich in clays, and it has a lot of organic and fossil material within it. My work in GeoSafe, I'm trying to look at the fluid flow through our rock types and how that evolves with different stress states. So in order for the GDF to actually be successful, we need to know that the geological barriers are going to isolate our waste from fluid flow. So we need to understand, as our GDF evolves over a timescale of up to 1 million years, we need to know if the stress state changes, how is the fluid flow going to change? So this is what I'm trying to characterize in my lab. Moving into a bit of the theory here, we're using a model that is traditionally soil mechanics, but we're applying it here to some rock types. So this is the Cambridge or CAM clay model. It's developed in soil mechanics. And what we're doing is we are putting a rock core, so represented here, under a confining pressure with a fluid pressure within it. So what we want to see is at what point this porous rock starts to collapse its pore network, where it starts to yield. So for porous rocks, there is a stress state where you have all of your confining pressures and your axial pressures are all the same, and your porous rock starts to collapse its pore network. So we call this the hydrostatic yield point. So this is called P star on this diagram here. If you're at what we call effective mean stresses less than your P star value, so if the effective mean stress, it's your 3 different stress directions, the average of that, and then you take away your pore fluid pressure. If you have your effective stress less than that P star, your rock won't fail just at hydrostatic conditions. It needs an extra axial load in order for it to start to fail, start to yield. So we apply a differential stress. So this is your maximum stress minus your minimum stress. So we have an axial load that we apply to our rock, start to compress it, and then at a certain point, that rock will start to yield. We find our yield by monitoring our stress response from the strain that we impose on this rock. So this is more like what the signal is on my actual computer when I'm running this experiment. I get a sort of acceleration up phase in the stress as I start to load my sample. That's when all the micro cracks in the sample are starting to close up. And then we get a linear elastic phase when stress responds linearly to imposed strain. There comes a point then when stress stops reacting linearly to strain and it starts to change, starts to evolve. This is what we call our yield point. So before the yield point, all of the strain is elastic, it's recoverable, it's like a rubber ball. If you squish it, it'll bounce back. But once we go beyond yield, because you're starting to collapse that pore network, it starts to become inelastic, it starts to become permanent deformation. We take all of these yield points that we measure at our different effective stresses and different differential stresses, and this should, in theory, map out the CAM clay yield curve. So this is what we're hoping to get from these experiments. So we have, in this CAM clay model, the theory is that at lower effective stresses, when your rock fails, it should start to dilate as it's failing, whereas at higher effective stresses, it should start to compact whilst it's yielding. There is a theoretical point in the middle, the critical state point, where there should be no volume change with yield. That's the theory. And then where your CAM clay curve, your yield curve then intersects the effective stress axis. That's where you get your hydrostatic yield point P star. Just to complicate it further, we can put a third axis on this graph. So it's been shown that the CAM clay model, these yield curves are sensitive to porosity of your rock as well. So as you increase your porosity, your yield curve gets smaller, your P star gets smaller, so your rock gets weaker. So if you're interested in looking more at this, Elliot Rice-Burchell, who was in our lab a few years ago, he did a lot of tests on rocks that had the same grain sizes, everything else controlled, but he changed the porosity of the sample and he saw how the deformation changed due to this change in porosity. But when we connect all of our critical state points for our different yield curves at different porosities, we get a critical state line. And something that comes up a lot in soil mechanics is when you connect up all the different P stars at different porosities, you get the normal consolidation line. That's something that they tend to measure more in soil mechanics. The permeability measurements that I do in the lab, we have a few different ways of measuring permeability, but the one that I'm using is pore pressure oscillation. So how we do that is we isolate one side of the rock sample from the control system, and on the other side of the rock sample, we impose a sinusoidal pressure wave. So in this diagram, it's the larger blue signal here. And what we're interested in is seeing how the sinusoidal wave changes as it passes through the sample. So we're looking at the phase shift, so where the peaks or the troughs of the wave, how much they are shifted in time. And then we're also looking at the attenuation of the signal, so how much smaller the amplitude of the signal becomes once it's gone across the sample. Believe it or not, this received signal would be really good for me because it's very low permeability, what I am measuring. So we do some processing. We've actually written some code, me, Dan, and Julian Mecklenburgh at Manchester. We wrote a code using least square spectral analysis in order to resolve the permeability. I won't put up all the maths here because there's quite a lot of it, but the Python functions are available on GitHub if you want to go have a look. Our partners at the BGS were concerned that we were using water to cool our rock preparation equipment rather than air, because with mudstones, they're very, very sensitive to wetting and drying cycles. So we didn't want to destroy the microstructure in these samples by using water in their preparation. So for quite a big chunk of my postdoc, we were trying to create the equipment in order to cut our rocks using just compressed air as cooling. This poses a bit of a health and safety risk because it then generates rock dust. So we had to come up with a design where we have a container for our pillar drill. So we have the rock inside our container, and then we have a dust shroud and a vacuum extraction system. So this seems to work really well, but it did take a while to get it up and running. But now we are managing to prepare samples, not just for me, but others in the lab as well. The machines in the lab, I apologize if you already know this, but we have high pressure and high temperature triaxial deformation apparatuses in our lab. So what we use these for, we can use them for hydrostatic pressure tests, permeability measurements, and also axisymmetric compression or extension tests. So we have in our pressure vessel, so this is contained within this safety shielding on the outside of the rig. We have our sample is this small section here, and this is the pressure vessel. And we use silicon oil as our confining medium because it's quite incompressible, so it's quite easy to get up to high pressures. So our maximum pressures are, I think, 250 MPa for our confining pressure. We have sample assemblies that allow us to connect the sample to our pore pressure and our confining pressure control systems. And then we also have, this is our axial loading column. So we have our force gauge is what allows us to measure the force acting on the sample. And we have a really large drive gear right at the bottom that allows us to apply our axial load to our samples. So step by step, how I go through my experiment methodology. At the start, I need to characterize my sample as best as possible. So dimensions of the sample, porosity measurements, XRD measurements, checking that it is fully saturated with the pore fluid, as well as I'm hoping to do some CT scans with Julia. When I've got my sample in the rig, I'm happy that it's fully saturated. I then start the yield curve probing technique. So what I do is at these different effective stresses, I start maybe at a low effective stress. I apply a confining pressure. It goes up this loading line until I find the yield point. Then I pull it back to hopefully avoid any permanent deformation. I increase the confining pressure. I do repeats. I load it up axially, find yield, drop it back down again, keep going up the effective stress axis. And the aim is to then be able to map out this curve of all the different conditions of yield. Whilst I'm doing that, we're also getting a huge amount of data in terms of things like pore volumemetry, how the hit point evolves. So each test so far is lasting around a month. So I have a lot of data from each experiment. The final part of the tests that I do is once we have mapped out this yield curve, is that then I want to see how the rock behaves, how its permeability changes when I deliberately force it past yield. So essentially, I take a condition, an effective stress, and then I go straight through this yield curve, and I'm monitoring the permeability throughout that loading curve. So we can see whether it dilates, whether it compacts, and then whether it starts to recover again afterwards. I put the challenges of the rock types because I wanted people to understand quite how difficult these experiments are. So the Ancholme Group rock type, I'm going to take you through first. It's quite a difficult rock type to work with, partly because we don't have much surface exposure in the UK and we don't have any core samples available. So we managed to get material from Must Farm Quarry down in Peterborough. The Peterborough Geological and Paleontological Group very kindly took me along, even though they were interested in the fossils, not the rocks. But we managed to get quite a lot of material from this quarry slag heap. But the material that we've got is extremely sensitive to wetting and drying cycles. So we're trying to keep it at the same moisture content that it is that we collected it at. It's also extremely fragile. If you sneeze near it, it will break. So it's very difficult to get an intact sample out of it. I'm going to run you through one of the experiments I've done on the Ancholme Group for this sample. So this one is a fairly typical one of the Ancholme Group samples I collected. So it's fairly high clay content, 47%. It has fossils within it, but not a huge amount. So it has about 16% of calcite and aragonite in it. And it does have some swelling clays within it. So it has a small amount of smectite within there. For the Ancholme Group, we found that if we went up through the cycles of effective stress, we didn't really find our P star point. So we think this might be because they are surface-derived samples. So we were struggling to find that P star, perhaps weathering has affected them. So what we decided to do was to set P star artificially ourselves. So for this one, I held this sample at 25 MPa effective stress. So this graph showing how the pore volume evolved, this is over 10 days. So it evolved quite drastically at the start, and then it sort of slowed down its evolution until it finally reached steady state after about 9 days. And then once I did that, I brought the effective stress down and I started mapping my yield curve. So the yield curve is shown here in this diagram. So we have the effective stress, P, on the bottom, and we have differential stress, Q, on the y-axis. You can see that if I compare this data to the theoretical yield cap, it doesn't really fit with it. It looks more like it's this sort of shape. So we have a very asymmetric elliptical yield cap. Now, this isn't a complete surprise. We have had previous measurements in the Rock Def Lab with a very steep limb, like a compaction limb of the yield curve. But this one is more pronounced than anything we've seen before. Once I'd measured that yield cap, so this is the same data here, I then loaded it past yield to see how it would evolve. So this blue line shows the stress path that load took. So you can see the response here of this is the axial stress that's responding to the axial displacement, so our strain. And the orange points are my permeability measurements throughout this experiment. So before I start the actual loading, the permeability is quite low. It's at about 3 times 10 to the negative 20 meters squared. And then as we start to yield it, we actually get quite a big increase in permeability. So just after the yield zone, we have a permeability that's 8.5 times 10 to the negative 20. But then after we've had that yield and we're into post-yield hardening here, the permeability actually starts to recover back down to near its original value. So this is a good sign for the Ancholme Group that at these sort of effective pressure conditions, even when the rock breaks, it can then seal up any fractures afterwards and decrease the permeability. So this is what we want to see in terms of a GDF. How the permeability evolves over time, with effective pressure. For the Ancholme Group, we see that generally as we increase the effective pressure, the permeability went down. And whether we were going up a pressure cycle or down a pressure cycle, the permeability was within error of each other. So once we'd set our P star at that 25 MPa value, then the microstructure wasn't evolving massively after that. Yes. Then onto the Mercia Mudstone Group. We have a different set of challenges for working with this rock type. One of them is that it is extremely heterogeneous. It varies a huge amount. So even on a small scale, this is one of my cores that I'm working with, and this varies a huge amount over just 20 centimeters here. But then it also varies on a basin-wide scale. So we have several different basins in the UK where the Mercia mudstone is found, and each one has a slightly different burial history and has slightly different structural history. So this is from Johnny McAvoy, and he's working on this aspect of the GeoSafe program. It also contains evaporite, so it contains gypsum, anhydrite, and halite. So there's a question over how does the gypsum evolve with depth in the subsurface? Does it convert into anhydrite? I did a lot of X-ray diffraction measurements with James for the BGS as our partners. They have been drilling some boreholes into their Keyworth site in order to use geothermal energy, I think, to warm the buildings there. So as part of our collaboration, we did some measurements of the mineral content of their Keyworth D borehole. So for these, they vary in clay abundances quite a huge amount, so between 0 and 63%. The 0% one, to be honest, is just a gypsum vein. I didn't even really need to do XRD on that one. I could tell from looking at it. But they do vary a lot more in content than the Ancholme Group samples did. The example I'm going to run you through now, it's still technically in the triaxial rig right now, but it's coming towards the end of this experiment now. So this one, I've got XRD measurement from the closest in the borehole that we have taken. So this one is quite strongly mineralized by gypsum. It's got 30% gypsum in it. It's got a much lower clay content than the Ancholme Group sample I showed you. It's only got about 13% clay content within it. I thought I'd show you some examples of the actual axial loading curves that I'm getting from these samples. So I showed you this diagram to show you the theory of it. this shows you the actual loading curves I'm receiving over their load point displacement. So we see a slight change in the gradient of our lines. So from the green to the darker blue, I was increasing the effective pressure. So we're seeing this gradient of the axial force to the displacement increasing. So from this, we're actually able to start calculating some of our poroelastic parameters. So the one I've got here is the Young's modulus. So as I increase the effective pressure for this one, we're estimating Young's modulus between 8 and 25 GPa, which matches up reasonably well with other mudstones. For the yield curve for this one, we've got quite a similar shape to the Ancholme Group curve that we saw before. So rather than the nice semicircle, we again have a very elliptical, asymmetric yield curve. I've highlighted one of the points in a darker blue color. This one was done at a much, much slower strain rate than the others, but it fits in with the same trend. If you look at the scale on this one, it's quite different to the Ancholme Group one I showed you before. So we're going up to 80 on the Q on the differential stress, whereas we were maybe at 5 MPa on the Ancholme Group one. I also did the loading beyond yield. This is technically for a different one, a different Mercia Mudstone sample, but I wanted to show it. So we see that the intact sample is up on the top left, and then after it loaded, after it broke, we had quite obvious macro fractures through it. So I gave the sample to Julia over in the SEM labs, and she did a micro CT scan of the sample, so you can see here. So it shows that we can actually see the macro fractures in this sample after it was broken. So when it reached yield, this sample strengthened a little bit more, but then its strength dropped massively. So this is when it broke into multiple fractured sections. So we have permanent brittle failure here. So before it failed, we had quite a low permeability. So that would have been for the matrix of this mudstone. Whereas when we have the fracture permeability, so once it's broken and we've got those fluid pathways through it, we've got a permeability that's 2 orders of magnitude higher. So this is perhaps not a good sign for the Mercia mudstone because it's not sealing its fractures and recovering from breaking like we saw in the Ancholme Group sample earlier. So I talked about comparing the different curves between our 2 different rock types. So I have the Ancholme Group as the blue at the bottom compared to the Mercia Group in the orange. So you can see the scale of difference in how strong these samples are. They do have different P-star values, but we can see just how weak the Ancholme Group is. I also put on comparison, we don't have very many literature sources of similar measurements, but there have been measurements by Silvio Geiger's group in Switzerland on the opalinous clay, which is the target for the Swiss disposal program. So I've put these points on in green for the opalinous clay, and they actually overlap quite nicely with our Mercia mudstone. It may be that they fit better with the Mercia mudstone sample because they're both recovered from cores, whereas our Ancholme Group sample is a surface-derived sample. So it may be that source of the different rock types, maybe that has impacted their mechanical data that we're recovering. So to compare the two, we found that the Mercia mudstone is relatively strong for a mudstone. It's got very low permeabilities when it's intact, but once it's broken, once it brittly fails, permeability increases by 2 orders of magnitude. For the Ancholme Group, it's the opposite. It's extremely weak, but it also has very low permeabilities, and it maintains the low permeabilities after it yields. So for moving forwards with further work, we've managed to measure permeability quite well in the dilatant side of the yield curve, but with our steep compaction limb, it's quite difficult to measure the permeability change there. So that's the aim for the next few experiments, is to try and get the permeability imaged for that side. How will this data be used? So we're trying to almost create a roadmap for our partners in Imperial College London. They have a geomechanics toolkit that allows them to simulate the GDF, and they can input lots of different parameters into this toolkit. So we're saying, for example, we have our current stress conditions. When we excavate the GDF, we expect the stress conditions to change to perhaps this value. So then those stress conditions would lead to this permeability value. Whereas if the stress conditions change in a different way, we know what permeability value that would lead to. So we're essentially giving our data as a roadmap for the modelers to then work out how permeability might evolve over potentially a long timescale up to 1 million years. I'd just like to say thank you to some of my collaborators. So Dan, Mike, Sam, Johnny, Julia, and then some of the people at Manchester who've provided the brine fluids for me. So Sam, Callum, and Max. And then also Andy and Andy at NWS for checking through my material for me. Thank you.
That was really interesting and really great to hear about. Do we have any questions?
The Mercia sample you chose, how did you choose it? I mean, you picked one that's rather low in clay minerals. So if you picked one that was a bit richer in clay minerals, it will have behaved quite differently, I guess.
Yeah, so
I don't know the answer to this, but I just thought I'd ask.
So this one, so for choosing the samples, at the moment, it's really difficult to get a sample prepared and put into the rig. So I've put 2 of the Mercia ones into the rig, and I've shown you both of them in this presentation. But because it's so variable on the scale of the cores, it's hard to know exactly what you're going to get when you drill into it, if I'm honest. Because, for example, the small core that I showed, go back. In this one, it varies within the core. So like I have reduction spots, I have like gypsum veins, I have such a huge variation on the scale. It's quite hard for me to target it to be trying to find ones that are high clay or low clay. This one, I don't know that we've been told which formation it's from in the cores that we've been provided. I don't think the BGS has scanned the cores, but I don't think they've told us which formation exactly they think it's from. I have the depths of the cores, but I don't think they've said which one. Yeah, it's borehole core, yeah. I don't know that they've told us exactly which formation it relates to. Yeah, but we haven't got all the data from them yet.
So
I'm not sure.
might have been sitting in a core store for a while as well. So it took advantage of the fact that they were drilling these new boreholes at BGS, and everyone's been distributed a certain section of that core essentially. So
Yeah.
it fulfills the criteria of being fresh and just being from the subsurface, but I think it still needs a little bit of work to figure out exactly where it is. It's a good point. Yeah, just within Mercia.
Yeah, they've collected a huge amount of data about it, but it's just they haven't shared it with us yet. I think they're still collating everything. This was drilled out like last year or something. The last few times we've been to the BGS, they were still drilling the boreholes. So it's pretty brand new material. Yeah. Yeah, I think so.
Cool. We had a couple of questions from Rob online. The first one was kind of related to what Richard asked as well, which was about heterogeneity and picking samples, especially from the Mercia. There's another one which kind of relates a little bit to something I was going to ask as well about the stress field and how that stress changes the criticality of rocks, especially things that contain gypsum and stuff like that as well. That was kind of related to something I was thinking about at the end of your talk. You're talking about how the stress state would change as you excavate these facilities. But then you talk about trying to model how the stress will influence permeability over 1 million years. What other processes are you expecting to change the stress state of these places once they're excavated over a 1 million year period?
Well, yeah, there's a lot of different things that are going to be incorporated into the model. So there's going to be considerations of temperature is going to be one thing as well, because putting the radioactive material in the subsurface, it's going to increase the temperature, they think, by a maximum of 150 degrees C. But then there's also, in terms of over 1 million years, what can change the stress state, thinking about long-term changes, like if there's changes in the climate, like if you have changes to glaciation and erosion and uplift, lots of different considerations of that, considering we were, in an ice age like 10,000 years ago. In another 1 million years, we don't know what sort of state the planet will be in at that point. So they're, I think, modeling quite a few different scenarios, which is why they want as much data from us so that they can, use it to inform, like if it's scenario A, then they'll have permeability B sort of thing.
Betty?
Sorry, this is just a very quick question. Well, first of all, Lizzie, thank you so much. It was a great talk. I really enjoyed it. And, something that I don't necessarily work a lot on, but it's great. Thank you. I just wanted to comment on the two different type of mudstones and the mechanical results that, you compared, and you said, one was strain hardening and then it became more permeable, less permeable again. And the other one broke and actually was very different. I mean, this might be a very silly question, and maybe I haven't really looked very carefully, but it seemed to me that the marine mudstone was oriented with very strong lamination perpendicular to the stress that you applied. I wasn't sure about the orientation of the layering in the Mercia mudstone, but it looked to me as if it could have been parallel to Sigma 1. Is that possible? And that would explain a lot of the difference, I think.
Yeah, so they are different orientations, you're right. So yeah, they are two different orientations. So the Ancholme Group one is perpendicular to the lamination direction, whereas this one is parallel to the bedding direction.
Okay,
so
you.
That may be something to do with it. So that's another thing I have to do in my further work, is do the opposite orientations to the ways that I've currently measured it. So yeah, we'll see if it makes it. We think it will definitely make a difference in terms of permeability, but it'd be interesting to see how it affects, the mechanical properties of it. Yeah, I think it'll be interesting as well at the different effective pressures, whether it's a low effective pressure or a high effective pressure, how those change, how they fail as well, because that should change their behavior too.
Pete?
Hey, it's very interesting. The Ancholme Group, I think, includes Oxford clay formation, Kimmeridge clay formation.
The Oxford clay is the one that we're looking at.
Okay, so because those are quite different lithologies, and the Oxford clay itself varies. I mean, as people have said, it's heterogeneous. And what you're showing there, I mean, I don't know what the white specks are in there, but they look thin shell bivalves, perhaps, or something like bioclasts.
Yeah, I have maybe two main types of, two kind of classification of the rocks that I've picked up. Some are fossil poor, some are extremely fossil rich. So this is one of the ones, this image is of the fossil rich one. But even the ones that I've classed as fossil poor, they still do contain shelly material like this.
Okay. So, I mean, it's exposed all the way up the northeast coast of Yorkshire. It's exposed all the way through the west, in various places in the Wessex Basin, and, that big strip through the Midlands. So there's lots of places you could sample it, and you probably should, I think, if you're going to do this, get an idea of what lithological variability it's likely to exhibit, right?
Yeah, I think it's, we have the PhD students working on the heterogeneity of the Mercia Mudstone. So they're like Johnny and then Holly over in Manchester. They're trying to, catalogue the heterogeneity of the Mercia Mudstone. And we have another PhD student, Tom Berry, in Leeds, and he is working on similar stuff to me with the Ancholme Group, but we don't have currently in the research consortium someone looking, we don't have like the equivalent of Johnny looking at the Ancholme Group yet.
Need a marine Johnny.
Yeah, we need a marine Johnny, that's what we need.
I think the less said about that, the better. Do we have any more questions, Ginny?
Thanks, Azzy. It was super interesting and really well explained. Thank you. So I had a question. You sort of described challenges and experiments and materials and things like that. And so I wondered, and obviously they're very time consuming to run, like they take a long time. So I wondered how good numerical models are at capturing or being able to explain experimental data at the moment, and what the prospect is for just running numerical models instead. It's because like there's going to be a limit in the lab to what you can measure, because you need to get your sample in the rig and everything like that, right? But if you're able to do a numerical equivalent, then maybe you would be able to take into account this sort of heterogeneity that you're describing, and like how good, I just wondered how good the numerical models are at the moment, and how your experimental data might be used for making them better.
Yeah. No, it's a good question. As part of our GeoSafe consortium, we have like a really wide range of different researchers. So I'm in one of the work packages. One of the other ones, they are taking scans, detailed scans of our rock samples, and they are modeling the permeability and the porosity of those samples to try and see how it varies between our measurements and the kind of theoretical permeability. And then I think there are also some numerical models on the adsorption of the radionuclides. I'm not a modeler, so I don't know like how advanced they are at this stage, but I know that we do have people in our consortium who are working on it. I know that eventually a lot of this material will get incorporated into the geomechanics toolkit. So I can kind of sort of answer, but not fully answer the question.
Okay, I think we'll leave it there. But again, thank you again, Izzy, for that talk and for closing out our series of seminars this semester.